Hi everyone. The title of this talk is What's the best place for an AI conference, Vancouver or blank? This work is by Google Research, and I'm Avishai Zaguri. The work was done with Einat Minkov, Idan Spector, and William W. Cohen. In this talk, I will first define the task of comparative question completion. I will explain our motivations and why this task is hard. Next, I will describe our dataset of human-authored relational comparative questions and how it was constructed. Beyond the contribution of task and dataset, we performed multiple empirical and statistical analyses. I will describe our results considering these two questions. Can pre-trained language models make sensible comparisons? And can language models learn to make comparisons via fine-tuning? I will conclude the talk with a summary and main takeaways. This work presents a new task, which is comparative question completion. For example, what is faster, a blank or a cougar? Or what is more loyal, a blank or a pigeon? Automatically completing such questions requires a combination of linguistic understanding, word knowledge, and common sense reasoning. These questions are human-authored. Users posted them on question answering websites. We masked one of the entities, and now the original slot filler. The first question compares the speed of a Great Dane and a cougar. The next question compares a parrot and a pigeon in terms of loyalty, and so on. We would like an automatic model to predict the masked entity. Of course, there are multiple entities that make sense as slot fillers, but some entities would seem nonsense to humans. For example, comparing the speed of a Great Dane and a cat doesn't seem right. Same for giving a rabbit as an example of a loyal creature, or comparing the size of the relatively small Belgium and the very large Russia. There are several motivations for automatically generating sensible comparative questions. In the context of human-machine interaction, comparative questions are an engaging element. They call for active participation of the user and can serve as a rhetorical method for shifting focus of the conversation. Because comparison completion is a complicated task, we also use it for probing state-of-the-art language models, where we can check how far these models go in terms of understanding language versus memorizing facts. In terms of related work, some works have shown that BERT and other large pre-trained language models encode factual word knowledge, including entities and their properties. For example, models like BERT can be successful in completing masked sentences like George Washington was born in blank. But the question is whether large language models can actually understand and reason with the text. Several works claim that the answer to this question is mainly negative. In our work, we challenge language models with the completion of human-level comparative questions. The main contribution of this work is a dataset of comparative questions which we extracted from question answering websites. We focused on three domains: animals, cities and countries, and NBA players. We used high-precision rules to extract these questions based on passing information and entity linking. In addition to entity mentions, we also mapped the questions to the compared entity property in most of the cases. So this slide details the most popular relations or properties in each domain. Users ask which animal is more intelligent, cute, clean, or strong. In the domain of cities, they ask about temperature, cost, and safety. And NBA players are compared with respect to shooting, clutch, and defense. Only a minority of these properties can be found in knowledge bases. Also, a large part of the relations is subjective and not factual. For example, cuteness of an animal. We must one entity mentioned in each comparative question, making this a fill-in-the-blank entity completion task. A subset of the questions in each domain was manually validated as comparative and non-offensive. We make these God-labeled test examples available. In addition to the test examples, we have questions that we use for training, which refer to different relational comparisons. As shown in the table, only a subset of the masked entity mentions are single tokens. In particular, in the domain of NBA players, almost all of the masked entities are multi-token personal names. We experiment with two language models in this work, hoping that they learned relevant knowledge in pre-training. The first is BERT, and the other is Relic, an entity-focused language model. BERT and Relic are not directly comparable. BERT can only predict a single subword at a time and uses a vocabulary of words. In contrast, our implementation of Relic has a vocabulary of the 1 million most popular entities in Wikipedia. This means that given a masked question, BERT predicts words and subwords, and Relic predicts entities. The pre-trained models were not trained on user questions. We therefore also fine-tune domain-specific language models using the training questions in the target domain. For example, we train BERT using 30,000 masked animal comparison questions, and we do the same for Relic, and repeat this procedure in each domain. Each specialized model is then evaluated on our God label questions in the target domain. So if we fine-tune it on animals, we also test it on animals, and so on. To evaluate the model's predictions, we use two evaluation modes. The first considers the original masked entity as the correct answer, where we report the performance in terms of a mean reciprocal rank. And we also report more comprehensive results, evaluating the top-ranked answers for each model based on human judgment. So here are our automatic evaluation results in the three domains using BERT. The pre-trained model results are in blue, and the fine-tuned model results are in red. We see that there is a large improvement following fine-tuning with BERT, but BERT is restricted to predicting single-word entity names. This is probably the reason that BERT fails in the NBA domain even after fine-tuning, since most of the examples in this domain apply to NBA players' names that are multi-tokens. Now we see that the results of the pre-trained Relic, which are shown in blue, are similar to the pre-trained BERT, but Relic gives more impressive performance following fine-tuning, since it is focused on entities rather than words. This has positive impact for all domains, and especially Relic also learned to predict the multi-token NBA player names. And this slide shows an example of the top predicted entities in the NBA domain. So the question is, who has more rings, Brian Scalabrine or Blank? Before fine-tuning, BERT predicted general words like me or you. After fine-tuning, it learned to predict NBA player names, but all of them are single token, like Kobe, Wade, Curry, and so on. With Relic, the results before fine-tuning do not make much sense, but they look quite good after fine-tuning, and even include the original masked entity, which is Dirk Nowitzki. We also report in the paper the results of human evaluation of whether the top predictions by each model make sense or not. Here, for example, we see that the fine-tuned models of BERT and Relic in purple and blue are both very accurate, but about 15% of the top results still do not make sense to human users. So far, we achieved good performance and comparison completion with the in-domain fine-tuning. The question is, did the models actually learn to perform relational comparison, or maybe they just learn entity in domain co-occurrence statistics? In statistical analysis, we found that the fine-tuned models mostly improved on popular entity names. The figure shows prediction performance on specific masked entity names by their popularity in the training examples, before and after fine-tuning. We see that prediction performance is mostly improved for the popular entities. On the right end, the most popular and rightmost entity is the United States. We also have interesting results that show that predicting the masked entity by its co-occurrence with the context entity in the training example gives very strong results. So even a basic statistical model can achieve really good results. And we also show that if the training examples are resampled such that popularity information is lost, then fine-tuning results go down, even below the entity co-occurrence baseline. In additional experiments, we also test the fine-tuned models across domains. We assume that if the fine-tuned models learn any general comparative semantics, they will improve also on out-of-domain examples. So these are the results. The numbers in the diagonal in gray are the within domain results, and the numbers in white are the cross domain results. As you can see, performance drops across domains. In fact, the cross domain results are similar and even lower compared with the pre-trained model. Our answer, therefore, is that the models do not generalize to other domains and only memorize domain statistics. To be fair, we extend the fine-tuning setup. Instead of training the models using domain-specific examples, we now fine-tune them using a lot of training examples that are topic diverse. We make sure that there is no entity overlap between the training examples and any of the test questions. We want to check if the models will now learn general comparison semantics rather than lexical information. Overall, we fine-tune BERT and Relic using more than 1 million topic-diverse examples in this experiment. And we get a single BERT and a single Relic model that hopefully learn general comparison semantics. The results are again negative. We see that in general, fine-tuning, which is shown in red, did not improve over the performance of the pre-trained models, which is shown in blue. In other words, the models failed to learn comparison semantics by fine-tuning. You can find more details about the work in the paper. And the main takeaways are we presented a new task and test sets. The task of predicting masked entity dimensions in human-generated comparative questions measures relational understanding and reasoning at standards of human interaction. We showed that fine-tuning achieves high results when trained and tested within domain. Still, predictions are sometimes perceived as nonsense by humans. And we showed that the model failed to learn general comparative reasoning using fine-tuning. Instead, they learn lexical phenomena. We hope that future work will start filling this gap. So that will be all. And there is more in the paper. And I hope you enjoyed. Thank you. Bye bye.